much easier chapter. And all these formulas at the beginning where it talks about electric flux is Q enclosed by epsilon naught. You have done that. I don't know if you remember. That is Gauss's law in electrostatics, but you don't really need all that stuff. Where it becomes important is this is a really important part. This is electromagnetic waves. And when you look at the diagram, you understand that an electromagnetic wave has an electric wave represented by the blue line there. And it also has a magnetic wave represented by the purple one. So E is the electric field, B is the magnetic field. So in an electromagnetic wave, you have a combination of both of these, the electric and the magnetic fields. And it's very important. This is one of the questions on the homework. You see the word synchronized. That means they are in phase with each other. You can write that down, note that down. The electric and magnetic fields are in phase with each other, which means they rise and fall at the same time. So if you look at this diagram, you'll see that exactly when the electric field becomes maximum, the magnetic field also becomes maximum. Then if you look at this point, when the electric field is zero, the magnetic field is also zero. So that's what you mean by they are in phase with each other. So they rise and fall together. But another thing is that they are in vertical planes. So if you look at the three axes, you see the X, Y, and the Z. You see that the electric field is in the XY plane. See that? It's in the XY plane, but the magnetic field is in the XZ plane. You see that you get the 3D perspective there. So although they are in phase with each other, they are in perpendicular planes. That's another point that you got right. So remember that the planes are perpendicular to each other. And the direction of propagation. So which direction is this electromagnetic wave traveling in? Can you guess, or can you tell me from the diagram? I know there's only two, but two is more than enough. Is it moving along the X, Y, or the Z axis, the wave itself? You don't want to try.
Is it the x-axis?
Exactly. Exactly.
Velocity?
Yeah, go ahead. Sorry.
Because of the velocity or the speed of light, c?
Exact, right. So
Cool.
C is the speed of electromagnetic waves, as you can see here, the green arrow, and it's moving along the X axis. So although the electric and magnetic fields are in perpendicular planes, the direction of propagation is also perpendicular to that. So what I mean is the X axis is perpendicular to the Y and the Z. We know that. Okay. So that's very important about electromagnetic waves. And what we normally call light, light is an electromagnetic wave. X-rays is another electromagnetic wave. So electromagnetic waves are divided into many categories based on their wavelengths. We're going to come to that. But this equation I want you to know. So let me explain this equation. So this is about the electric field. So E sub Y, and you know that the electric field is oscillating along the y-axis. So as a function of x and t, that means at any point on the x-axis at a particular time, if you want to find how much it's moving along the y-axis, then you have to use this formula. This is the peak value. E naught means peak, means the maximum. E naught is the peak value. So note that down. K is called the wave number. K is the wave number. And K is actually 2 pi by lambda. 2 pi divided by lambda. You may remember that lambda is the wavelength. So K is the wave number and it's 2 pi by lambda. Unfortunately, I was not able to connect the iPad to this. Otherwise, I would have been writing, okay? But I'll repeat many times. Omega is the angular frequency and it's 2 pi f. Omega is 2 pi times f, where f is the linear frequency. So those are the terms there. I'm not going to ask you very complicated questions on that, but you just need to know k is the wave number, omega is the angular frequency. That's all you need to know. Similarly, you have a very similar formula for the magnetic field. So if you want to find how much B is at any time, and it's BZ because you see that it's moving along its oscillation is along the Z axis. But the terms are the same, exactly the same, except that B naught is the peak value of magnetic field, which is this one, and everything else is the same, okay? And that is a very important formula. You may be asked a question on that, and a direct relation, E naught is equal to C times B naught. E naught and B naught are the peak values, and C is the velocity of electromagnetic waves. So E naught is equal to C B naught is an important equation, where C is the velocity of electromagnetic waves. Do you know what the velocity of electromagnetic waves is by any chance? Remember, I told you light is an electromagnetic wave. So if you know the speed of light, that's the speed of electromagnetic waves.
3 times 10 to the 8th meters per second.
There you go. Perfect. 3 times 10 to the 8 meter per second is the velocity of all electromagnetic waves. Okay, so here is another formula that you must know. And this time I'll let you make a formula sheet. That's good news, isn't it? You can write any formula that you want, and that also for the final exam. I'll let you make a formula sheet. So you can just write this down. C is 1 by root mu naught epsilon naught. You remember what mu naught is? Mu naught is the permeability of free space. That is a magnetic property. And its value is what? 4 pi times 10 to the negative 7. So mu naught is 4 pi times 10 to the negative 7. Epsilon naught is the permittivity. So one is the permeability, the other is the permittivity, and its value is what? 8.85 times 10 to the negative 12. 8.85 times 10 to the negative 12. And sure enough, if you put that into the formula, take the square root, 1 by that, you're going to get 3 times 10 to the 8 meter per second. You can check it out later on. That's exactly what you're going to get. Oh, yeah, I should. Why did I have to shout all this? It's coming up. I didn't know. Here. Okay. Mu naught, I gave it to you as what? 4 pi times 10 to the negative 7, which is exactly the same thing, which is 12.57. You know, 4 times pi is 12.57 times 10 to the negative 7. They put it as 1.2 times 10 to the negative 6. The same thing. And if you are interested in the units, it's farad per meter and Henry per meter. Henry is the unit of inductance. Okay, Henry per meter and farad per meter. And I'm recording this for your sake and for the others. So everything will be there when you come back. And please feel free to stop me at any time when you don't understand anything. And I will never be insulted, okay? I can repeat it twice, 3 times, 4 times. And then again, C is 3.00 times 10 to the 8 meter per second. Any questions there? That's fair enough, right? Clear? Okay. This is another very important part, and you got to be very careful here. The electromagnetic spectrum has many regions, but you have to be careful. You have to notice lambda is the wavelength, and if you go from left to right, the wavelength is decreasing. That's what you have to know. This is 1,000, isn't it? 10 to the 3 is 1,000. So radio waves have a wavelength of from 1,000, not exact values, from 1,000 to about 1 by 1,000. You see, 10 to the negative 3. So all those are radio waves. But in between the radio waves, there's also a region called microwaves. Hence the name microwave oven, because that thing uses these wavelengths. And again, you need not memorize the exact wavelengths, but just have a general idea of where it begins and where it ends. So note that down. You have to generally know. Does anybody know what infrared means? What's the common name for infrared rays? That's what I thought. Heat rays. Heat is nothing but infrared. Okay, heat rays. So when you have any hot object giving out heat, it's nothing but infrared. So just write that there. Infrared means heat waves. What's the meaning of infra? Infra means lower. So infrared waves or heat waves have a lower, you can see its frequency is lower. Now be careful on that. The wavelength is higher, but the frequency is lower than that of red. Let me say that again. Infrared rays have a lower frequency, but a higher wavelength than red. Why are we talking about red here? Because the next region is the visible region, and it starts with red. Oh, it's magnified here. You can see it, red all the way to violet. Remember the colors, the 7 colors of the rainbow? That's what we're talking about. So then after a while, so it's really funny, maybe not be funny, but it's really interesting. That is only a very small region of the electromagnetic spectrum that we can see. Look at the, this is drawn to scale, and look at that. That's only the region which the human eye can perceive. We cannot see heat rays. Neither can we see radio waves or microwaves. And then the next one is ultraviolet. The word ultra means higher. So what's higher? The frequency is higher. The naming is based on frequency. Just remember that. The naming is based on frequency. Ultra means higher. So ultraviolet here, it's higher than that of violet. And then you have gamma rays. Ever heard of gamma rays? I'm sure you have. Gamma rays are radioactive radiations that are really very harmful, very penetrating. They can penetrate the chromosomes and create mutation. You know that genetic mutations can happen. That's one of the after effects of, although I don't like to say it, Hiroshima and Nagasaki, where the atom bomb was dropped. Even now, babies are born with defects because all those who did not die, their grandparents, they were exposed to these gamma rays, and mutations took place, and that is carried on to every generation. You know that, right? So that's the unfortunate event. That's why we do not want another country. We didn't know at that time. We can't excuse ourselves, but we didn't know at that time that it would cause such a big havoc. Okay. And then did you notice that X-rays come in between ultraviolet and gamma? So there's no particular demarcation. So this region, you can call it ultraviolet and X-rays. Look at that. Is that making sense what I'm saying? So it's not clearly divided. Okay, I won't go into the details of that, but I also want you to know the wavelengths of visible light. Very important in the medical field. You have to know that violet has a wavelength of 400 nanometers. Violet, 400 nanometers, and red actually goes to about 750 nanometer. So just know that 400 nanometer wavelength of violet and 750 that of red. You can see that although this is 700, red extends till here. Okay, so infrared will have a lower frequency. Oh wait, lower wavelength. I have to be careful, isn't it? Am I right? No, think
So
about it.
red would have a higher wavelength than
Okay,
purple.
infrared, yes. Red would have a higher wavelength, so infrared has even a higher wavelength than red. You can see that on the scale. So that's one of the questions I'm going to ask on the exam, as to how, which wavelength and all that. So I'm just giving you any questions on that? Nope. Okay, so here is the reason why I've been telling you that if the wavelength is higher, the frequency is lower. See, look at this formula. C is F lambda. So the product of frequency and wavelength gives you the speed, which automatically means that frequency is C by lambda, isn't it? Frequency is C by lambda. So one is in the denominator, the other is in the numerator. So remember, if the frequency increases, the wavelength decreases. Okay, they're exactly opposite because the product should always give you the speed of light. Oh, here it comes. Low frequency means long wavelength. See, low frequency means long wavelength. High frequency means short wavelength. Yeah, that's what I've been trying to say. But when you see it in writing, it makes so much more sense. Yep, I told you visible light is only a small portion of the electromagnetic spectrum. Really, really small portion. And now we will look at the properties of the different regions. And certainly you have to know this because most of you are going into the medical field. You really have to know what's coming next. Yep. These, like I said, I'm recording it. Don't memorize, but you have to know. I'll ask you questions where I'll give you a property. You have to tell me which one. Like if I ask you, can ionize atoms, which one? Ultraviolet. Which one can produce photoelectric effect? Well, of course, ultraviolet produces sunburn. We know that, right? We do know that. Even with my dark color, if I stand out in the sun, I become darker. That's interesting. And if I think you all know that it's the melanin under the skin that gives the color, right? The melanin. So anyway, sunburn is caused by that. I just went a little bit deeper, that's all. What is photoelectric effect? Photoelectric effect is when light falls on certain materials, electrons come out. That is the photoelectric effect. Gabriel wanted to ask a question, I think. No? I thought you were trying. No. Okay. Stop me whenever you have a question. You all know what ionization is? Removing an electron or adding an electron to a neutral atom. That's called ionization. So ultraviolet light, if it falls on certain atoms, they can remove electrons, making it an ion. X-rays, well, who doesn't know about X-rays? You know, X-rays can pass through many substances, but cannot pass through some others. Yeah, it can go through tissue, but cannot go through bones. Why? Because tissue is made of lighter elements like carbon, hydrogen, and all that. But bones are made of calcium and phosphorus, right? Which are heavier. So X-rays can go through tissue, but not through bones. And then that also lets the doctors see the inside internal organs of humans and animals. Before X-rays, they had to cut open. Yep, it's true. If a child accidentally swallowed a pin, they had to cut open. And you know, the discovery of X-rays is an accidental discovery by a scientist called Willem Röntgen. It was totally accidental. Because we don't have the time, I'm not going into it, but it's interesting. Read on that. He didn't know what it was. That's why he called it X-rays. Remember, in math, what we do not know, you call it X. That's exactly what happened. But very useful. Well, especially when you go to the dentist, X-rays, right? But that has to be for a real short time. Otherwise, it's dangerous. Okay. So from ultraviolet to X-ray to gamma rays, are we going to the higher frequency side or the lower frequency side? It's right before your eyes.
Higher.
Okay. And when the frequency increases, the energy also increases. Note that down. I'm going to give you a formula. Higher the frequency, higher the energy. Now that explains why ultraviolet light is not as penetrating as X-rays, which means gamma rays are very penetrating. It says there, it's the highest energy photon. Photon is a light particle. You can write that also. P-H-O-T-O-N. Photon means a light particle. And man, I forgot what PET is. proton emission tomography. Do you know what PET is? I forgot. No, it's positron. It's positron emission tomography. Ever heard of it?
Yeah, once.
Yeah, because PET scans are used with CAT scans to give you a 3D picture of the internal organs. Isn't that fantastic? Because if you use only one of them, you get a 2D picture. But if you use both, and then you can get a 3D picture, which means you can know which organ is how much behind and all that, gives you the third dimension. I think I'm talking too much. So that's gamma rays. Okay. And now we're looking at the other side. We're looking at the other side, low frequency, long wavelength. Yeah. Infrared, I told you, hot objects radiate light at this frequency. I don't like that. Well, it should be radiate heat at this frequency. Uh, Let me ask you a simple question. When something is heated, when you begin heating it, it does not produce any color, correct? But as you keep on heating it, it becomes red hot. Now you know why we call it red hot, because it's beginning to emit red. What happens if you continue heating it? Then it will emit even the other colors. And if you really make it hot, it becomes white hot, because white means it's producing all the colors. Okay. So really hot means white hot. Okay, another thing. I'm just connecting in my brain. My brain is beginning to work. A flame, we always want it to be blue, right? Now you know why? Because if it's blue, then it's very hot. Because red is a little bit hot and blue is like very hot. And white hot, that's the sun. Our sun is white. Okay, it's the sun is actually emitting visible light. In case you didn't know, it's emitting heat. That's a joke. It's also emitting ultraviolet, so it's emitting everything. It's a full spectrum. Microwaves. Microwaves, I want to tell you something. Probably you knew this. How does the microwave oven work? You cannot put metals inside. That'll be the last time you ever use it. So how does it really work? It produces a range of wavelengths, which are called microwaves. But what is interesting is these are exactly the wavelengths that water loves. It's the resonant frequency of a water molecule. So that means if you allow these frequencies or wavelengths to fall on a water molecule, they will just take it in. They will grab it. They like it. It's the resonant frequency. So when you have food, normally you have water molecules spread all over, isn't it? So now what's happening is that means the food is getting uniformly heated because the water molecules are spread all over. I hope you remember that sometimes we try to use a wet napkin with some food, right? This is the reason, because we know that unless there is water, it's not going to take in the heat. That also explains why metals should not be put inside. Metals will not at all absorb this. Instead, they will start reflecting it. And the reflection gets focused and there will be fire there for sure. Don't even try it. Okay, so that's making sense. Microwave. So whenever I say these things, you know that exam 3 is kind of different because it's not, there is going to be problems, but there's going to be more of ideas and concepts because of this chapter, which is a good thing. Radio waves, yeah, radio waves, it's television uses a part of that, cell phones use a part of that. There is an international body that actually divides and says these wavelengths are for cell phones, these wavelengths are for television, and so on. Okay, so that entire thing is called radio waves. They are very low frequency. That means they are very low energy, so they do not affect human beings. Because right now when we are talking, we are being bombarded by so many radio waves from different stations. They don't touch us, they don't hurt us. Microwaves, they will hurt us. Infrared, yes. If you keep going to the higher frequency side, they hurt us more. Okay. Any questions? No? Oh, I'm perfect. That's why. Okay. All right. Energy density. I don't think I picked a homework problem using energy density, but you can write it down just in case I go crazy. What do you mean by energy density? Let me define it. Energy per second per meter squared. Energy density means energy per second per meter squared. So that's energy density. So the unit would be joule per second per meter squared. So, and these are the formulas for energy density. Average energy, U is the symbol for energy density. So the average energy density can either be calculated using this one, epsilon naught E naught squared, or B naught squared by mu naught. Since you're making the formula sheet, you can write it down, but on the formula sheet, you cannot write down what each one stands for. Okay. I'm going to soon post an announcement that'll make it the textbook. No, you can write down the symbols, but you cannot say E naught stands for peak electric. No. All right. So on the left side, you have the formula for energy density. On the right side, you have the formula for intensity. We can just limit ourselves to energy density. You need not write down intensity, just energy density is what I'm going to ask you. Okay. Oh, they've given two other formulas too. No, there's no need. All right, here is a part that you will be definitely tested on. Now, remember, a photon is a light particle. I told you that. And the energy of a photon is given by the formula. Hopefully, they're giving E is equal to, oh, they did not yet. Okay, I will go by this. The energy of an electromagnetic wave comes in packets. That packet is called a photon. The packet of energy is called a photon. And what's the speed of the photon? Same as the speed of light. This is what I was looking for. Energy of a photon is H times F. That's the energy of a single photon. H is a constant. It's called Planck's constant. There it is. Planck's constant. The constants will be given to you, but it's okay if you write it down. 6.626 times 10 to the negative 34 joule times second. F is the frequency in hertz. Oh, they didn't give the unit. F is the frequency, means number of oscillations in a second. E is the energy of the photon. So that'll be an easy question, but there will be 2 or 3 steps. So we will get to that in a minute. Here is a problem. The only problem that is being done here, and a very important one at that. It won't be asked exactly like this, but yes, if you understand this question, you will be able to do any problem in this section. So let's look at the question for 1 minute. Oh, they're giving you the steps. So the photon of wavelength 646 nanometer is absorbed by an atom and re-emitted. During this process, the photon loses 1 electron volt of energy. So that's a new unit. Electron volt is exactly the charge of the electron, joules. That's the charge of the electron. What is the wavelength of the newly emitted photon? So what is actually happening? The yellow one is the photon and it's hitting the atom. The atom is absorbing the photon and then emitting it at another wavelength. So the incident wavelength is 646 nanometer, which is the wavelength of this one. And we are asked to find the wavelength of what comes out. All right, so you got to draw a diagram that's label all quantities. Yeah, that's in any physics problem. So lambda naught is given 646 nanometer. So why delta E? Because it says the photon loses. So that's not energy, that's the change in energy, which is what students miss. Again, that is not the energy of the photon, that is the change in energy of the photon. The change in energy of the photon is 1 electron volt. And we are asked to find the wavelength uh, of the photon when it comes out. I hope you're getting it so far. Okay, if we continue, this is the formula that I told you about right now. The energy of a photon is HF. And then we also know that frequency is C by lambda. Because remember, F times lambda is C, same thing, just rearrange. So substitute that in place of F, and you get E is equal to HC by lambda. And then substitute the values. H is Planck's constant, it's right here. C is the speed of electromagnetic waves. Lambda, you can't have it in nanometers, so you got to remember nano is 10 to the negative 9. So 646 times 10 to the negative 9. When you do the calculations, you get this number in joules, because that's, so we got the energy of the incident photon. That's what we got. We got the energy of the photon that was falling on the atom. But now we know that the change in energy is 1 electron volt. So the incident energy is there, E naught. And so we can find the final energy now, of course. Didn't it say it loses energy? Yes, it said it loses. So what we'll do is, to get the final energy, we will subtract the 1 electron volt from these many joules. But technically, you cannot subtract electron volt from joules. So we'll have to change this into joules and then subtract it from here. Okay, so that's the idea is change is final minus initial. And so final is when you rearrange initial minus the change. Notice that in place of 1 electron volt, you have 1.606 times 10 to the negative 19. So that will give us the final energy. And once you get the final energy, you've got to work backwards now. So it's a process. And then find the final wavelength. Okay, so this is the third step now. So once again, we use E is equal to HC by lambda. Now we have the final energy. Just plug in the final energy. We know the values of H and C. Make lambda the subject and calculate. There it is. So lambda is HC by E, where E is the final energy of the photon that comes out finally. And then when you do the calculations, you get 1,347 nanometer. Notice that the wavelength went up. Obviously, that means the frequency went down, which means the energy went down. Yes, it did lose energy, so that is correct. 1,347 nanometer. I may not ask you a question that has all these three steps, but when you understand this problem, surely you can do anything that I ask you for sure. Okay, so now reflection. I don't know if people do this, if you get time on the exam to think about the answer, this is what they're doing, looking at the significant figures, and I don't try to focus too much on sig figures. I think really I must, but then the grades will come down. So I don't, but they're trying to say if there are 4 sig figures in one and 3 in the other, then the answer should have 3, So that's what they're trying to say. Do the units make sense? Lambda is in nanometer. Yes, it does. Does the number make sense? Yeah, already discussed that. Yes, the wavelength. How did you lose energy and gain wavelength? I already told you. Correct? When it loses energy, the frequency goes down, which means the wavelength goes up. That is why. There it is. So everything is correct. So there you have the summary of the chapter. Wow, what a short chapter, right? Simple, sweet chapter. And I looked at, wait, I can't get all right, I got it. I looked at the homework before I started this lecture. Give me a minute to see if I covered everything. I did. Remember, I told you that electric fields and magnetic fields are in phase. Did I tell you that? That's one of the questions. They are perpendicular to each other. That's another one. Oh, I forgot one. Do electromagnetic waves require a material medium to go through? Think about the sun. I just told you, and we know that the sun is emitting electromagnetic waves. And there is miles and miles of space where there is nothing. But yet, all of these waves come through. That means electromagnetic waves do not require any material to go through. Note that down. They can just go through space. Electromagnetic waves can travel through space. It does not require any material. I mean, that doesn't mean that if there's a material, it won't go through, okay? Of course, it passes through air. Sometimes I have to be careful in what I say. And I just wanted to ask you, do you think that the sun is producing sound? The sun at its source, its nuclear fusion and fission in the sun.
How would we hear it if sound can't travel through a vacuum?
Okay, good question. So my question was not, do we hear the sound? My question was, is it actually producing sound? All right, imagine that you could go to the sun. You can't, not at this time, but imagine if you were near the sun and there was no space between you and the sun, and if there was only air, would you hear the sound is my question.
Yes.
Okay. I know where you're a little confused. I'm with you on this. How is sound produced? Anything vibrating produces sound.
It has to vibrate through the air.
But the vibrations will come through air. If there was air, it will come through air. But the problem is there's nothing, so the vibrations don't come through. That make sense? Or did I confuse all of you? Sense. Yeah. So actually we are being saved. If there was air all the way, life would have been impossible on the face of the earth. We could not have heard anything else. We would have been hearing the rumbling of the sun day and night. Nights, I don't even know whether we could sleep. Anyway, you know what I mean. So since it's space, we are protected. That was something, that's another problem, question actually. All right, one more question. You remember a capacitor? You know, a capacitor can be charged. And between the plates of a capacitor, we surely know that there is an electric field. Don't we know that? Yeah. But I want to tell you that because that field is changing, there is also a magnetic field. So in summary, between the plates, write that down, in between the plates of a capacitor, you have both an electric field and a magnetic field. I think I addressed most of the homework questions, you know, trying to make it easier for you to finish the homework. This is one chapter that will get you a grade up because fewer formulas, more ideas. So be sure that you study the electromagnetic spectrum, as it is called, all the regions, and look at how they affect the human body, what are their uses and all stuff like that, you know, read on that. Okay, do you have any questions? Anything?
This chapter was easier.
I know, see, wait until we get to light. When we get to light, there's one chapter where it becomes a little tough, but reflection and refraction of light are easy. The problem is some students don't last until then. I can't help saying it because, you know, we start with waves. Remember waves? And then it's downhill actually. So the next two chapters are, the next chapter is easy, but the one after that, is a little bit complicated, but not as tough as the chapters in electricity. So we have easier chapters. And remember that for the final exam, I will be giving you, well, it's going to be comprehensive, but I'm going to give you a nice review. It doesn't mean that the same questions will be repeated. No, no, no. It only means that those topics will be addressed in the final exam. All my other classes, it's around April 15, but for you, I put it on April 25th. The reason is all of these chapters will be there. All the chapters in the sense, all chapters are done after exam 2. So that means we will do the other 2 chapters also, is what I mean, before exam 3. And then we'll come back for the final exam with everything. Am I making sense? Yeah. So yeah, I pushed exam 3 a little further away, so we get time to finish the remaining 2 chapters, is what I mean. So we'll be done. When you take exam 3, we're done. And then final exam, we'll have review. I hope then more people will show up, and because the reviews are going to be important, Right? Anything else? Okay. You don't want to hear my ranting, like waste of time. All right, then we'll see you next Tuesday.